So what we'll do now is we'll take a look at a couple worked examples. And this will be kind of typical of what I expect you to do on the homework and also on the exam. And we're just going to be focusing on single phase applications. And so the first scenario that we have is we've got a scenario where I've got a surge that's traveling down an overhead line. And we're not really concerned right now about how that surge got there, but this is going to be characterized by a magnitude and a duration. And so it's just a square pulse, 500 kV, and it's going to have a duration that's going to be given by 10 microseconds. So somehow this got generated. Later on, we get in the lightning analysis, we'll show how something like this could be created by a lightning strike. But anyway, we've got this scenario where we have the surge traveling down the overhead. And what we're concerned about is we're concerned about what happens when we hit this discontinuity that's going to be given by this cable section right here, where it hits 0.1, and then this is going to travel down a length that's going to be given by 1,000 feet, and then it's going to hit a load, and let's say the equivalent load resistance looks like 200 ohms, and this would basically be kind of like what we think about the surge impedance of the load itself. If it was a pure resistance, that would be 200 ohms. So 1,000 feet doesn't really seem like much, but when you're looking at these waves traveling at the speed of light, yeah, it's going to make a difference. So anyway, as far as the data that we have, the overhead line has a surge impedance that's given. It's given at 300 ohms, and the cable has a surge impedance of 50 ohms. The load, as I said, had a surge impedance of 200 ohms. And then what we're given is we're given the velocity of propagation. And so the velocity of propagation for the overhead line is 980 feet per microsecond. I'm doing this in terms of feet. Normally when you do these calculations, it's in terms of meters per second, so you'd have to convert. And then the velocity of propagation of the cable is given by 400 feet per microsecond. And the reason that cable has a slower speed is if the velocity of propagation is 1 over the square root of LC. We've talked about before where cables have more capacitance. So as the capacitance goes up, 1 over square root of LC is the velocity, C becomes bigger, the velocity of propagation goes down. And so these transits travel actually slower in cables than they would like an overhead. And so we want to take that into account in doing our calculations then. So what we want to do in this case is we want to go ahead and figure out what's going to be happening at 0.2 as a function of time, and also what's going to be happening at 0.1, all right? And then we'll verify the result with an EMTP simulation in the third segment of this lecture. Okay, so as far as the hand analysis, the way I would normally approach something like this is I would start off by redrawing the circuit, and usually what I would do in this case is I would just kind of lay out what I want for the nodes. Basically I would start maybe reworking the terms if needed. If I had like L and C, I would have to calculate velocity of propagation for that. If I had an LC, I can calculate surge impedance. In this case, I gave you those values directly, but I would usually just kind of redraw the circuit. And then what I would do at key points is I would start to calculate then what are the reflection, refraction coefficient, the delays that's going to be used in the pulse bounce diagram. And so first thing I would do is get the time it takes for the waveform to travel down the cable. This is the line length divided by velocity of propagation. So if I had 1,000 feet, I divide by 400 feet per microsecond, and I get a time tau of 2.5 microseconds. So it takes that small amount of time for that, basically that waveform to shoot down that cable. Now I'm going to want to know when that overhead surge hits this discontinuity, then basically what's going to get refracted, what's going to continue to go down that cable. And so I'm going to need to have this refraction coefficient at 0.1. And so that's refraction coefficient, that gamma B, is 2ZB divided by ZA plus ZB, where ZB is the surge impedance of the cable and ZA is the surge impedance of the overhead. So that refraction coefficient is 0.286. So 0.286 of whatever hits from the overhead side is going to continue to go down that cable. Now, when I hit the load side, I'm going to get a reflection at that. I'm going to get a reflection at 2. And this is going to be gamma A2, which is going to be ZB minus ZA over ZB plus ZA. So it's 200 ohms minus 50 over 200 plus 50, which is 0.6. And the thing you ought to be thinking about would be, well, what would be worst case? Well, the worst case in this case would be this when this is an open circuit, because basically that would give me a reflection coefficient of 1. Something else I could also calculate would be if this waveform, once it hits the 200 ohm load, it's going to reflect back toward the overhead, and there's going to be another reflection coefficient at 0.1, which is going to be ZB minus ZA over ZB plus ZA. Now in this case, ZB is the overhead, ZA is the cable. So 300 minus 50 over 300 plus 50 is 0.714. So basically what's going to happen is once that overhead waveform hits that cable, it's going to be traveling back and forth. It's going to be bouncing back and forth. I'm assuming that overhead is sufficiently long where I don't need to worry about a reflection from the far end of that overhead. So we're just modeling what happens right after that surge finds its way into the cable section. So now that I've got all the pertinent reflection refraction coefficients, and what I would do is I would work up my pulse bounce diagram. So the pulse bounce diagram, again, this is distance from 0 feet down all the way at the end of the cable, which is 1,000 feet. I've got it calibrated on the vertical axis in terms of tau, which is the travel time for the cable. So this waveform travels down the cable, and it's going to take a time tau to get there. This tau is the travel time for the cable. Just keep that in mind. So it's dependent on the velocity of propagation for the cable. What I would have is I would have the 500 kb waveform come in from the overhead, and when it hits that discontinuity at the cable, we use the refraction coefficient of 0.286. So 0.286, which I put over here to the left hand side just for bookkeeping, 0.286 times 500 is going to be 143. Note when I do these pulse bounce diagrams, what I usually do is I show how I get the number, which is like the refraction or reflection coefficient times the incident waveform magnitude. Then I usually also show the result. So that way, if I'm debugging, I kind of know where that 143 came from. So anyway, I got 143 kV. It's going down toward the 200 ohm load. Once it hits that 200 ohm load, then it reflects back with the reflection coefficient of 0.6. And so what I have is I have 0.6 times 143 being sent back. Now, what's the voltage we see once that waveform hits the 200 ohm load? Well, I have to take the 143 plus the 85.8. It's a summation of those two, right? So that's what I would have in my diagram. When I see this reflection coming back, this 85.8 kV waveform, then basically what it's going to do, it's going to see a reflection coefficient of 0.714. So 0.714 times the 85.8 gives me 61.3 reflected back toward the load. Take that, multiply by 0.6, it goes back toward the left, have another reflection coefficient, and it's going to go back to the right. So I'm doing this for a relatively short period of time, and what I need to do is if I'm calculating what the impact's going to be at either end, I basically have to add all the voltages up as they change. And so if I wanted to know what's going on here, it'd be the 143 plus the 85.8 plus the 61.3 plus the 36.8 plus the 0.714. I've got to do the bookkeeping. I got to keep track of all those different values, right? We can sketch this out. We can sketch out what this is going to look like. And so if we're at the sending end of the cable, this is going to be this first diagram. If we're the sending end of the cable, I got 143 kV that I can see at that point. And when the reflection comes back, what I need to do is I need to add 85.8 plus 61.3. And so what that's going to do, it's going to be the 143 plus this plus this. This is going to give me 290 kV. If I'm looking at the receiving end of the cable, well, up to time tau, I don't see anything because the waveform hasn't hit yet. So there's a time delay. And so initially at the end of the cable, I don't see anything. But after a time tau, the waveform hits the far end, hits the load end, and then basically I get 143 plus 85.8, which is the 228.8 here, kV. And then what happens is that it travels down back toward the source side, reflects, comes back down here, has another reflection. And to get this next change at the load side, what I need to do is add 143 plus 85.8 plus 61.3 plus 36.8, which is going to add up to the 326.9. All right. So when I talk about 4 tau, then basically 4 tau is going to correspond to the 4 times what I had for the propagation time, which is the 2.5 microseconds. All right, so anyway, if you keep working with that, then what you can do is you can fill out the rest of the diagram. Normally what we're concerned about is we're normally kind of concerned about what's going to be the peak values. And what you could see in this case is that basically what's happening is that this receiving side is basically kind of starting to charge up if you think about it that way. So if I had a 500 kV voltage that's going down the line, and say if it stayed at 500 kV, that eventually that would have to charge up to 500 kV. That's kind of like the source voltage in this case. However, one thing you have to watch out for is that this waveform only has a specific time duration. So after 10 microseconds, that source voltage goes down to 0, right? And so what you have to do is you have to take that into account in your calculation. And that adds kind of like another wrinkle for doing the math on that. Typically when we do this, we don't really kind of worry about what happens after the 10 microseconds. Typically any damage that's going to get done is going to be done by then. But one way you could actually model something like that would be you do the pulse bounce diagram assuming a 500 kV source, then after 10 microseconds you add a minus 500 kV source. You use superposition. So that's kind of a trick you could use if you're working this by hand. But typically I won't make this too complicated for you. I usually just have you guys run this out to 1, 2, possibly 3 tau in terms of what's going on. Otherwise it just starts to get pretty complex. So anyway, this is just kind of a simple sort of example to start with. A more realistic situation would be, though, is looking at a full switching surge. And so here's an example. We're basically applying the same techniques, but what we're doing is we're doing this at a distribution level. And so we have a single phase, it's 12.47 kV line circuit, and we're basically energizing this at the source side of the circuit. And we'll assume in this particular case that we have an overhead section, we have a cable, and we're trying to figure out, well, what are we going to be seeing at these points on the circuit, points A, B, and C, and then what's going to happen to this 500 ohm load. Again, I'm given the surge impedances. I'm not giving you L's and C's. I'm just giving you the surge impedances and the velocities, right? And these are given in terms of feet per microsecond because I'm giving you lengths in feet. But a lot of times if you're entering this into like PSCAD, you have to usually get these into usually some metric system number, you know, like meters per second, something like that. So anyway, we're basically trying to do something similar to the previous problem, but now you can see what I need to do is I need to model the source effect as well. And what I'm told in this case is I'm told I've got a pre-insertion resistor with a value of 300 ohms. Now, why would I have that pre-insertion resistance into the circuit? Well, if I just simply applied that source directly to the overhead line, then basically I'd have the full value of the source voltage being applied to that overhead. And so basically I would have this waveform traveling down that would correspond to possibly 7.2 kV RMS, so multiplied by square root of 2, you can get the line to neutral peak value. But that waveform would be traveling down the line, and that might cause too much stress on the cable or might cause too much stress to the load. So what I can do is I can put in what's called a pre-insertion resistor, and in this case I have a pre-insertion resistance of 300 ohms. Now what's so magic about 300 ohms? And I'm going to take that out after a time, but as far as the initial transits, I'm going to have that in the circuit. Well, if that overhead line impedance is 300 ohms, basically what this gives me is it gives me a voltage divider. So I'm going to have the 300 divided by the 300 plus 300 or 600. Instead of having that full voltage applied to the overhead, I'm going to cut that in half. And so this is pretty common on overhead systems, especially on transmission, where you use these pre-insertion resistors at the very, very beginning in order to kind of damp out or trying to cut down on the peak values of voltage that we would be seeing in these types of circuits. So in this case, you just have to plot this out for a time period of 3 microseconds. And so when you work in this problem, this is a little bit more condensed, you have to set up a pulse bounce diagram again. But note in this case it's a little bit more complex because I have a left side of the circuit. I got a midpoint between the overhead and the cable, so that's why I have that point B line, and then I've got the cable. And what you see here is I've got this set up in terms of tal AB, where tal AB corresponds to the velocity of propagation on the overhead. So this is going to be faster than what I'm going to see on the cable. And then basically this doesn't get from the beginning of the overhead to the end of the underground until quite a bit of time later. So basically in this particular case, what has to happen is it's got to propagate down the overhead at time tal AB, and then it takes another 2 times tal AB because the velocity of propagation in the cable is like 2 times what it is on the overhead. It takes a little bit more time before it finally gets down to the far end. And so anyway, you can take this into account in your diagram, where these dashed lines have to take into account the fact we have different speeds on the overhead versus the underground. I don't have the dashed line shown here in this case. So anyway, you got the time for going down the overhead of 0.51 microseconds. The time going down the cable is going to be 1.02 microseconds. So basically, when you add both these numbers up together is where you get the total travel time going from the far left side to the right. The source voltage magnitude, if I have a 12.47 kV line to line, divide by square root of 3 to get that line to neutral, multiply by square root of 3 to get that, multiply by square root of 2 to get that 0 to peak. So it's 10,182 volts. And again, what gets injected on the left side because of the pre-insertion resistor is going to be 300 divided by 300 plus 300 times 10,182, which is going to be half that voltage of 5,091. So probably not a big deal on distribution, but it would be a bigger deal on transmission, especially higher voltage transmission. So anyway, I can go ahead and I can calculate all the various reflection, refraction coefficients. Note what I'm doing at the middle point is I'm calculating a reflection coefficient for what's coming down the overhead. I'm calculating a refraction coefficient for what continues to go down the cable. I'm calculating at the far end a reflection coefficient as well as a refraction coefficient. And then what's interesting about this, if I have a waveform going back toward the source, if I had that pre-insertion resistor there, the reflection coefficient at the source is 300 minus 300 over 300 plus 300 is equal to 0. So another nice thing about matching the impedance of the pre-insertion resistance with the surge impedance of the overhead line is that basically I don't get any reflection coefficient, any contribution back from the source again once the switch is closed. So anyway, this is the diagram. I didn't go through as much detail as I did in the previous example. You can kind of play around with this on your own. But basically you see the 5091 propagating down the overhead. We basically would multiply this by the refraction coefficient of 0.29, give us the 1476. The 1476 times the reflection coefficient of 0.82 gives us the 1210. And then what you can see what's going to make this analysis complicated is that when it hits the midpoint, you basically have a reflection coming back from the midpoint, and then part of that goes back toward the source side again. And so when you have these multi-cable systems, to do this by hand starts to get pretty complicated. So anyway, just kind of a quick sketch of what this is going to look like. And this is what this will look like at point B and also at point C. And I didn't really run this out too far because, again, this analysis is kind of hard to do with all the different waveforms you have to do the bookkeeping for. And this is where we'd like to have computer programs. So the by hand analysis isn't something you would typically do on the job. This is just more to give you an understanding how this works, and then we can compare this against the PSCAD and start to kind of see how the simulation would kind of match up a little bit more by the theory, having worked parts of these by hand first. All right, so the next thing we'll do is we'll take a look at these examples mapped over into PSCAD.